Alright, so this is a great question. This one is not on the test, not about clock radios, but it's about calculators. In fact, there's two on there about calculators on the actual test. The one about what's the probability of finding all four being defective, or all five in this case being defective. And then we have this idea, this one has this idea of at least one. Right? At least one is the key words out of this whole statement. So remember that the probability of at least one meeting something, the opposite of that is none, right? The opposite of at least one is none. So we use that idea of complements, which is 1 minus the probability of none. Right? The probability of at least one is the probability of one or more, right? And one or more things happening. And the probability of 0 is the only other probability left. If we add those two up, they add up to 1 every time, because that's the probability of everything, one or more or 0 things occurring, right? Those should add up to 1, so therefore if we take 1 minus P0 or P of none, we get 1 or more. Alright, so let's find the probability of none of them being defective. Alright, so the probability of none being defective, alright, we have 7% of these 8,000 clocks are defective. Let's go find out what that is. Alright, so 8,000 times 0.07 gives us that we have 560 defective clocks, and then that means that we have the rest of them, 7,440, are all not defective, no defects. Alright, so we're going to take a sample of 5, and we want to find the probability that none will be defective. Alright, so we're going to take from this batch of this 7,440, and we're going to expect to have one good, let me restate this. 7,440 divided by 8,000 is the probability, that's the probability of getting one good, right, one good one is 7,440 divided by 8,000. Alright, so if I take 7,440 divided by 8,000, I get, that's the 93, and we kind of knew that already. We knew it was going to be 93 because it was the opposite of 7% are defective, so 93% are not defective. Alright, but remember the other thing about this is it says without replacement. So for this particular problem, we're going to have to do this this bit here where the probability of the first clock being good is 7,440 divided by 8,000. Then the next time we have one less good clock and one less clock overall. Alright, and we're going to find out if in this problem, because as we talked before, if you have really large numbers like this and you're doing a lot of them, we can treat it as if the events are independent when they are in fact dependent. But just to be thorough, I'm going to do it this way. Alright, so we're going to put all these numbers, remember we do this all the way down. So these are our chances of getting 5 good clocks in a row. Every time we pull out a good one, we reduce that by 1, and of course the number of calculators in the box or in the batch is reduced by 1. So let me get the calculator out again and figure this out. Alright, so notice what I did there. I put all the numerators in parentheses divided by, and then put parentheses again, all the denominators. And we get 6956228, blah, blah, blah. And let me just show you, let's assume we said that this was not without replacement, that it was with replacement. We could do 0.93 and raise it to the 5 power. And let's just see what that gives us as far as that goes. And you see the numbers are the same all the way out to 4 decimal places. So even though this says without replacement, because these numbers are so large, this number is so close to 0.93, the second and the third and the fourth, fifth numbers are all close to that, so it's a good approximation. So anyway, what we do now is we take 1 minus this 0.6956. Right, that's the probability of no defective calculators in a batch of 5. So 1 minus 0.6956, I'll go back to my small calculator, and we get 0.3044. And that is answer choice D.